All right. So in of the morning we discussed before. Then now we listen to Luca, who's coming to tell us on the DUNE experiment and possible near detectors, probably also the sand detector.
Yeah, probably, for sure.
Okay, for sure. All right.
As you will hear in a moment.
Great. So, floor is yours.
Okay, thanks a lot to the organizer for the invitation. I'm very happy to be here today. And I understood that my task is to convince you that neutrino physics is a very good, excellent asset for the muon colliders. So to convince you of that, I have first to, describe the physics of neutrino from my point of view in a very rather general way, to convince myself, first of all, that neutrino is extremely important in the particle physics scenario. And allow me to be rather generic, not only general. I think we have three big issues in high energy physics. Well, the first one is the dark universe. We do not know about the characteristics of dark matter and dark energies. Here it's my pleasure to show this is the range in terms of Z of redshift of Euclid. I was also a participant, collaboration, part of a collaboration Euclid that was launched 2 years ago and now is collecting data. And we will have the first release for cosmological purpose in about 1 year from now. And we know possibly better what is the situation about the evolution of the universe in terms of dark energy. Just on the same subject, the dark universe is there. And you should be totally convinced by this Planck result they are a few years ago, where you see the cosmic microwave background depicted by the cluster of measurements from local to large. You see, this is not a fit. This is just, this is not a fit of lambda CDM, but it is how it comes out of the measurement itself. So dark universe is there. And the second question is about the flavors. Just to remind people that we have the quark sector and the lepton sector. The quark sector is described by Bekabaibo, Kobayashi, Masukawa, and the lepton sector is described by Pontecorvo, Maki, Nakagawa, Sakata. And you see here by these boxes, by the largeness of the wideness of these boxes, that the two metrics are quite different. So this is, and also clearly it's the mass distribution of all these elementary particles spans about 12 order of magnitude. And I would say that the flavor question also, finally, it deals with the fact that we have 26 parameters, at least 26 parameters in the standard model. The 6 quark masses, the 6 leptons, the 4 elements of the mixing matrix for the quark, the 4 from the PMS, and then the 3 gauge coupling, the X mass, the strong CP. And if I forgot the boson mass, one boson mass. So flavor, just to give you an idea, quantitative idea of what we are talking about, you see how much diagonal is the mixing in the quark sector, while in the lepton sector, we do not even know what is the hierarchy of the free mass state of neutrinos. We do not know, as also Chris mentioned, we do not know if we have this configuration, this pattern, this ordering, or the other one. The only thing that we know is that the neutrino mass should be around or below the electron volt. And the last question, the last big question is the presence of antimatter. Where the antimatter went is a big question, because clearly there was a tiny imbalance in the mass and antimass in the early universe. This is disappearing as far as universe evolve, but the charge parity violation that would be a source, origin for a cause for this asymmetry in between mass and antimass, was established for neutral current in 1964, then for the B in 2001, then for the D decays in 2019. But in any case, we know that it is in the CP violation in the quark sector is too much small for describing this huge imbalance. So the question is, what about the lepton sector? And if we recollect these three big questions, neutrinos can be used to give some answer. Okay, clearly about antimatter, sure, because the next coming experiment, DUNE hyper-K, they are supposed to be able to measure the leptonic delta CP phase. So we should have an idea if the lepton sector is able to give some hints about this imbalance. About the flavor problem, we need absolutely, I will show you how much quantitative we need to measure the Ponte-Covro macchina cagata saccata matrix, because we are far from the precision of a quark one. And finally, we may measure something unexpected, and this could be hints for the darker questions. We hope to find something unexpected. We don't want to find everything coherent with a standard model. So we don't want to rediscover the Higgs in the leptons sector. And just to remind you what was one-way conclusion in the very recent European strategy particle physics, Venice 1 month ago, less than 1 month ago. This is the sentence: neutrino physics was emphasized as a key area given their potential for ground-breaking discovery. So I hope this gives you some suggestions how much important is the neutrino physics, how much important is to pursue the dedicated effort and experiments to this field. And okay, I will tell you more. So about the neutrinos, there are many neutrino sources. You can see here in terms of the energy and in terms of cross-section. These are all the different sources, which you all well know. And about the fluxes, there are very huge fluxes from the cosmological up to the cosmogenic, where the accelerator lies. Okay, I draw this by my hand. I think is more or less correct. We are here, essentially, in terms of fluxes and energy. What about the cross-section? Coming back to, so there are huge fluxes, but fortunately or unfortunately for a physicist, fortunately for the humanity, the cross-section neutrino is very small. As is, on top of that, it's not well determined. You see here the two basic interaction, the charge current with mu and the charge current with an electrons. And you see this is a recollection of all the measurements. Immediately by eye, you see that below, or even if you want above 100 GeV, the measurements are very fuzzy, are very, I mean, they are not very details. This is the reason, one of the main reasons, or one of the three main reasons why we are with the present scenario of neutrino experiments, even Hyper-Kamiokande and DUNE, we are stuck. So if a muon collider with a store arranger that can produce neutrinos can improve this, all this measurement neutrino cross-section would be not extremely interesting, it would be fundamental. I don't like a new storm, by the way, too much on this game. Because we need much more control statistics, detectors, and in any case, I'm not so optimistic about the new storms. Cross-section 2, this is, there is also another complication some way about the cross-section, is that there are three main concurrent interactions. One is the charge current, but I show you the Feynman diagram, the deepness scattering, this red one. But there are also the rather low energy, but rather low, it depends. Below 10 GeV, there is the quasi-elastic part, the red one, and the resonant part, the blue one. So it's very difficult to make a measurement because it's very difficult to modelize. There are a lot of parameters. If you look at one of the most, a la mode generator like Genie, there are hundreds of parameters that describe all these situations. So the model also is extremely complicated and limited. And of course, everybody knows that there is an interplay between the measurement and the generators. Only if you have an infinite precision detectors, you can forget about the Monte Carlo generator. So there is still always an interplay. But to have the best detector, as also Chris outlined, this is very important. To have the best detector with the best energy resolutions would be extremely important. So just one slide to remind you that after the announcement of a possibility of the neutrinos, when it took about 20 years, a little bit more, in 56, how the neutrinos was observed the first time, they plus a detector 200 kilo of water and 20 kilo cadmium chloruro, closer to our reactors, and they could observe the anti-neutrinos and measure via the inverse beta decay. This interaction of the antineutrino, electron antineutrino, produce a prompt positron and a delay about 5 microsecond neutrons. The neutrons is delayed and captured by the cadmium, and then it is it further release a photon. So you can detect the photon, and from the time calibration, you can measure the presence of this antineutrino interaction. So the history was actually not so simple after 56. Why? Because until 1998, nobody knew that the neutrino have masses and they could oscillate the membrane. Even if Pontecorvo, although Pontecorvo in 57 said, but the neutrino can oscillate and can have also some sterile contributions. It was, nobody thought about that. And the fact that they could oscillate in some way. And also that we are facing mass state and flavor state. This was not at all clear at the end of the last century. Okay, if you want just an explanation, you can read my short paper of about 10 years ago. So the recent history after the 1998, there was the first observation that the neutrino oscillate. From the atmospheric one, you expect a certain number of new mu from the proton interaction in the atmosphere. In Super-Kamiokande saw that we were missing a part. And then actually at the same time, a reactor experiment named the SHOW looked for the same effect in the electron-neutrino part. And he didn't find anything. He didn't find no disappearance. Super Kamiokande found a disappearance in the muon part, in the new mu. SHOW found nothing. No disappearance at all. So what does this mean? It took about 3 years, not so much, but to understand, after Snow observed the oscillation in the disappearance in the solar part, and also another reactor, but with a very large, SHOW was about 50 meters, sometimes from meters from the reactors. Kamaland was on average 150 kilometers from the reactors, and they observed disappearance. So, if you put all together the observation, the short, long, for the muon and the electrons, it came out almost straightforward away that you have to deal with masses, mass state, and with flavor states. And so we come out with Pontecorvo, Macchi, MNS elements. And 10 years after, we lost 10 years here. Because actually this SHOW could measure θ13, but we lost 10 years because the calibration, the money of SHOW was not sufficient. Just, I mean, this is one part of the story. But we measured θ13, and we are waiting for 2 other things, just to measure the delta CP and also the mass ordering. So this is a panorama. These are the 3 mass states, these are the 3 flavor states, and these are the experiments that can measure different. You can decouple, rewrite the mixing metrics in this way, and these are experiments that tell you results on the mixing θ23, θ13, and the θ13 and θ23, θ23. Okay. DUNE, what can do DUNE? I mean, I don't want to politically incorrect, but DUNE would be the only one of the 2 experiments that could measure everything in one single experiment. How much is important? It is relevant. Why? Because we have a lot of constraints, like the cross sections, and I will show you immediately another one. It would be important to measure everything, all the mixing angle and delta CP and the mass hierarchy in the same experiment, because we have a lot of unknown, unconstrained things like cross sections that tell you that there are things that we do not understand. So this is the first asset of DUNE. And why things are also even very complicated. Because, I mean, this is the appearance of from the neutrino mu from the accelerator, and they are observed in electron neutrinos, and you see how much complicated is the expressions. Everything is handled by the L or by E. The length, the distance between the source of the nu mu, where the nu mu are produced, and the interaction. This is very well known parameter. What is not very well known is the energy of a neutrino. Neutrino have very low cross section. That means that you need very large detectors. If you want to deal with very large detector, your resolution is very poor, for sure. Wotan-Cherenkov or scintillator is extremely difficult to have a very performant detector, very large and performant detector. It wasn't very costly. So DUNE is trying to do this. This is not only a brute force, but it has a detector, a liquid argon for the first time, that can have a rather good resolutions in energy, because this is the point for measuring the oscillation. Another things that I wanted to address here. Since you have this very complicated expression, it is clear that inside your result you may have this very quite natural degeneracy. Also, because your energy resolution is not so good, you may have several possibilities of degeneracy. This is the main reason for the near detector. You have to measure the fluxes, the neutrinos, in two different sites along the path, near and far. So they really oscillate. This is Cameland. I like a lot to show this. Cameland results. And you see how much this is no oscillation one, and this is the disappearance, so survival probability of a disappearance effect. We improved a lot in the last 20 years. You see here the parameter theta 2 3, theta 1 2, and theta 1 3. How much we didn't know anything about theta 1 3. There was also some theoreticians were thinking possibility it would be 0, but until 2012, then you see how much now is one of the best angle measured, and this is the situation. I mean, a few years ago, but it doesn't change too much of delta CP as well as delta M31. So we improved a lot, but we do not improve sufficiently. And this is, remind you, this is a mixing matrix. This is how it deals with the present situation, with present measurements. So this is the joy and the torment of all this physics area. What do we know and what we don't know? Chris already went through, so we don't need to go. Just one thing that I want to address would be extremely important, as has been done for the quark sector, to check the unitarity of a matrix, because if the unitarity is not there, that means that you have more than 3 neutrino masses. So we are far away. DUNE hyper K altogether with measurements and even with the reactors, we provide you theta 1 3. We can have some, we can try to put some constraint of unitarity, but not a very well robust measurement. Measurement delta CP are quite far away, so you skip, but extremely important. I would like to point to this Fukujita and Yanagida 1986 paper, which tell you how through leptogenesis, how you can link the delta CP to the universe issue. But in any case, the message is that it is mandatory to measure the delta CP. However, to measure delta CP is not like to measure something very easy. In the case of X, you know, the X mass was predicted by the Nextly-Dinora electroweak effect, right? 1993, EPS Marseille. They measure for the first time the Nextly-Dinora electroweak, and they said, okay, so they are perfectly described by the standard model, so we can perfectly say what is the range of the X masses. And actually, they were right. And they discovered the X where it was more or less supposed to be, and perfectly consistent with the standard model constraint. However, in the case of the neutrinos, these are, for example, a contour plot of correlation between the mass splitting of the third and the second, mass state, and theta 2 3, and the mixing, the same mixing angle of the two. And you see what is the error band. They are very large. But also, if you put together two different experiments like NOVA and T2K, they are in contradiction. I mean, they are contradicting themselves. Because in the game is entering also the possibility of one ordering or the other ordering. And in one case, for example, this is the result is compatible between NOVA and T2K. NOVA is the cartoon, the zone, the area, the color area, while T2K is the ellipse, and this is the same. This is in contradiction. And actually, last year came out T2K and NOVA with a lot of difficulties put together their results. They tried a combination. They didn't figure out. There are possibility of neutral or normal ordering, possibility other result for inverse ordering. There is no clear result. So situation is confused, to say. But it is a few years that it stays confused. Therefore, we need absolutely the new step and the new experiment like T2K and NOVA. And this is, I have no time to speak about the anomalies coming from the neutrino, serine neutrinos. There could be a fourth mass state here at the electron volt scale. This is an old indication for Los Alamos. Famous Los Alamos experiment, but there are hints and there are tension against between the disappear, the muon and the electron neutrinos. I mean, one experiment see a presence of a sterile, the other one not, and so, and they are not consistent. So the present scenario is that we are still quite far away from a very robust measurement, especially for the mass hierarchy. This is the most important thing because we want to set the matrix, the oscillation matrix. We are really far away. And we probably have to wait at least 5 or more years to have a robust measurement that means 5 sigma measurement. Just to convince you that the situation is complicated, let us see how the ordering and the phase, the delta CP phase, works inside an experiment like NOVA and T2K. This is the number of antineutrinos against the number of neutrinos. Japan wants to make the opposite, number of neutrinos towards the number of antineutrinos. You see there are ellipse of blue one. This is a normal hierarchy. The red one is the red one is inverse ordering. The ellipse give you all the possible value of delta CP from 0 to pi. The two ellipses goes in different directions also, and there are two different ellipse blue because we don't know what is theta 2 free, what is which octant it stays theta 2 free. These are the bands a few years ago, but this is not changed too much. To make a measurement, and you see also the ellipse are changing for the experiment for NOVA and for T2K. Why? Because of the energy of the beams. The energy is playing a lot of the energy of the beams, the neutrino beams, in the way in which this ellipse behaves. So my message, it is mandatory to measure both hierarchy or mass ordering and delta CP in the same experiment. Because we have a very loose constraint of the energy and the resolution of the experiment. So if you want really to disentangle the different parameters, to have one experiment is an asset absolutely mandatory to me. So this is, hyper-K will not be able to measure my mass hierarchy because it's a short baseline. I mean, not short, but it's a rather short baseline compared to DUNE. DUNE will be able to measure both. and have to be consistent. There should be a point here and not a completely out measurement. This is just the counting part of the experiment in terms of neutrino and antineutrinos. Yep. Which conclusion? Your? I don't believe it. I don't. This is no. I was believing that 10 years ago. When I discovered the scenario is completely cumbersome, it's very fuzzy. Or you have a very performance detectors. If you combine 2 sigma, 3.5 sigma, 3 sigma of Juno, no. I mean, and this my conclusion comes from the fact that T2K and NOVA have different results. Why? I mean, this is a big problem. So if you put together also Juno, for example, in 4 years or 7 years from now, you will not get anything of robust. The present knowledge, I would say only one experiment that measure DUNE, that mass ordering perfectly at 5 sigma, and this would be DUNE. This is no way out. So this is a key question. Somebody tell us that the mass order is more important than the delta CP. Delta CP, well, I don't know. I mean, theoretician can tell us. But I mean, the mass order, because my hope is that they are inconsistent in the PMNS scenario. If they are inconsistent, you see from the ellipse, if you can find out something, that there is something strange that you do not understand, you have to change the model totally. So just to coming back to this ellipse, this is T2K, NOVA, and this is the average situation of DUNE. E per K will be nothing more but a larger T2K, same baseline, same beam spectrum, same detector technology. The difference between DUNE and NOVA, there will be a longer baseline, wide band beam, and very improved energy reconstruction. And why the wide band is important, why the beam energy is a key issue, is that you see that if you take the lowest energy, the lowest part, lowest interval, this is the beam foreseen for NOVA, for DUNE, you see how the ellipse behaves. In the central part, they are far away, and in the highest part, they look in this way. But to be able to disentangle these 3 different scenarios, you have to be able to measure the energy very well with a precision of 10% or something like this. And there is, up till now, no experiment that was able to measure the energy of a neutrino with this precision. So DUNE, what to measure, how to measure, when it will be available, is a multi-billion project between 3 and 4 billion of dollars. The beams go from 1 to 2 megawatt, more or less. When we start oscillation, this is the latest prediction, just decided 2 months ago. So we hope that it is the final one, 1932. 1932, we will have the first beam. The key feature, you more or less, I skip it. We are talking actually is quite a complicated project like LHC, and the experiment of LHC. So we are talking of the facility, LBNF, and the experiment. They are 2 different projects. And this is how it works from Fermilab out to South Dakota. There are 1,300 kilometers away. And these are some reference. And these are oscillations, how it will appear by phase detector. You may be surprised by the fact that here we start from the muons, neutrino muons. And then we come out with muons and electrons and a very large fraction of new taus. Unfortunately, the energy is too low to have neutrino taus. You may compute what is the minimum energy to detect the taus? 3.7 GeV. So you need an energy beam of like CNGS of about 20 GeV to produce the tau. So you can only measure neutral current for these taus. Okay. The facility with a near detector is about 600 meters, more or less, 300, 500. And you see this hill because you have to pick up the right angle. And here there's a location of a near detector that will be inside the Fermilab campus. These are, since we are talking of fluxes, these are the fluxes foreseen. They are wideband, but we have to be able to measure the energy as best as possible. And this is one possible observation. We don't have so many events. You see here, after 3.5 years, we are talking 100 events. So any synergy, again, with muon collider would be extremely wonderful because you don't need only 100 events. You need 10,000 events for a very big, very nice measurement. SURF is the far detector site. Excavation is completed. You see situation in January, but this is finally has been completed. And they also will be available in 6 months from now, and we are going to build the two far detector building. Near site, we have one, we just said that 2 months ago that we have a delay 1 year more above the previous schedule because we have problems with the near detector. We are a near site facility in terms of, essentially in terms of money. The role is extremely important. The near detector actually is a complex because there are different detectors. And now I'm focusing on that. We will have 3 detectors essentially. 2 of them are coupled because you have a liquid argon, multi-boxes, and followed by a muon spectrometer because you can, to contain the muons from the charge current interaction here, you need you would need a 20-meter long, a very long detector. So you just couple this part of a few meters with this muon spectrometer, and these 2 detectors can move in the transverse directions because this is the flux when you are on axis, perfectly orthogonal to the beam. But if you move away 15 meters or 30 meters, like here, then you see that you have less fluxes, but in a more refined, in a more low range, low interval energy. So it is in principle, it is easier if you have a large, big variation of the energy band. You can, in principle, is possible to measure better the energy and the energy of the neutrino interactions. This is a situation when the 2 detectors are moved. And then we have a third electron that stands all the time on axis. This move transversally every 1 week. Sand will stay there. And let us see, okay, we see his requirements must monitor the beam change on a weekly basis. First of all, we have to be sure that the beam is not, the fluxes are stable. Should provide independent measurement of flux, flavor content. You have to see, in one of the previous slides, I've shown that there are different contributions to the beam. You see here in the FSC version, so forward or current, you see that this is this is a neutrino nu mu, and the anti-neutrino nu mu are almost 1 order of magnitude, is a few percent. While in the case of the anti-neutrino productions, the nu mu, the red one here, you see that above a certain energy, they are of the same number of production. So you may have a very important contribution from the conjugate neutrinos, and you must be able to disentangle. Liquid argon does not have any magnetic field, so it's not able to disentangle, but the possibility to detect the Michel electron, how at the end of the electron, the muon the decay. While sand will be able to measure because it has a magnetic field. So we'll be able to distinguish the flavor. And I mean, I cannot say because I'm presently the project leader of this sand, but I think that it will be extremely relevant for DUNE because it will be it is a multi-purpose. It measures almost perfectly the energy, and it operates in magnetic field. And you see here the precision that we can achieve in all this energy interval is extremely good, a few percent. About systematics. How it works, this measurement, why linear is important. So as far you are measuring, for measuring delta Cp, you want to measure the appearance of the nu E and the appearance of the anti-nu E. Delta Cp comes out when you have a quantum interference between two different frequencies. So we have to measure two different appearances. These are the numbers. You see the number of neutrinos of electron in appearance over the number that you are expecting. This is the probability. And this for the appearance of nu mu, this is the probability of the appearance of nu mu. What is important is not only a counting experiment, because there is this dependence, that there is the energy. You have, as I showed you before, you have to be able to measure the energy. At near, you are providing the expectation of the denominator. But the number of the events that near you are able to measure and then to predict at the far is a very convoluted expression. It is the oscillation itself, you don't care, it's about 1. You suppose that it is 1, a very short distance. It depends on the flux, sand will be able to measure. It depends on the cross-section. And we have also a liquid argon target to constrain as much as possible the cross-section in the liquid argon. It depends on the response, the physical response that interplay the neutrino energy, the true neutrino energy with the visible one, and the response of the detector that interplay the visible energy and the reconstruction energy. We will be able to measure also this factor, but the only thing that we will not be able to measure, because we don't have sufficient liquid argon, is the detector response in liquid argon. So we are not able to disentangle the visible energy with the reconstruction one. But of all the rest, sand will be the only detector experiment that will be able to measure almost everything. Somebody out of the record, are you convinced that this could be an important issue? No, because fortunately we have very good large detector operation in an operation like, for example, Icarus. We will have we have already million of events. So we know at the first order clearly what is the response of the neutrinos, muon neutrinos in liquid argon? How they are reconstructed with this, which precision and with which capability. So we are in a very bad shape. The conclusion, my conclusion, surely this is not DUNE conclusion. This was done, this is a slide for the INFN, so take with care. No near detector means no DUNE significant result. You have seen the error bands of the cross sections. This means that you need to compare near and far, absolutely. You need the near. No SAND, no reliable near detector data because only SAND can disentangle the flavors. SAND will be on the floor the first day of the beam data taking. This is also an important asset because it comes from mostly from an existing detector, and will be, this is true, this is absolutely true, one of the best detector ever placed in a near site of a neutrino beam. You can think of all the cumbersome situation on T2K, on NOVA. NOVA was a smaller replication of the far side, but the resolution was as it was, scintillator and ion. So building from scratch would not be possible. It will be extremely costly. We are talking more about 200 millions of euro or dollars. So fortunately, we are getting this experiment from an existing one. This is the Chloe experiment, where we pick up a superconducting solenoid magnet and electromagnetic calorimeter. And the only thing that we have to build from scratch is the inner tracker, because Chloe has a very light drift chamber that for sure has no mass, essentially useful for neutrinos, so there will be no neutrino interactions. We could only be used because we have this is the liquid argon part is 1 tons of liquid argon. Neutrinos are coming from the side. You can only use, you could only use the tracker for the reconstruction of events, but you want also neutrino events interaction in the tracker. So you have to optimize the need for a massive detector and the need of a light detector because you want to reconstruct the particles. How this is obtained? Is obtained putting together thin layers of very dense matter like graphite of CH2 together with very low density chambers that could be straw tube or drift chamber. And this is still not decided things. And this is how it would like a particle level in one full spill of the DUNE of LBNF beams. This is how it looks like. When you see these levels, you gated, you reconstruction, when you gated, you see that we would be able to measure very well the interactions everywhere. So this is the schedule. 10 minutes left. Or give me 5 minutes. This is the schedule. Very that has been updated. You see, in 32, we will be able to have beam. The near side facility will be decided. The construction. We have still to sign the contracts. That's the point. Keep by yourself. But for probably INFN, no. The point is that before to start the construction of a near side facility, we need to sign the contract. This is what is foreseen. We hope not to have too much delay, but then we have beam line that will follow. But we need the all to start the installation. So we have only 2 years and 2 years and a half to start installation. SAND will be able to do it, okay? Because all the parts are essentially there, but the tracker module will be, we are thinking that could be installed once the sand is already down in the hole, in the detector hole. The collaboration, I don't know if you know, is very large for the 200 institutions, 37 countries, plus CERN. And this is how large would be one of the two detectors that will be placed in the near site. This is the neutrino from Ferbila. This is the enormous cavern that I showed in the pictures. And this is, we have actually two phases. I don't think it's important to go through today. This is the description, I mean, the liquid argon, but I would need still half an hour to describe you some liquid argon characteristic. In any case, DUNE phase 1 is also enjoying a lot of activity from a prototyping phase. This is done as at the neutrino platform at CERN. So maybe you have heard about that. We have two very large liquid argon detectors, one with a usual standard single phase, and the other one was a modified double phase where the cathode are rotated 90 degrees. And as well, there is a very rather important prototype going on at Fermilab for the one of the liquid argon near detectors. Perspective, my last slide, I think. So just to reiterate what has been discussed before, these are the experiments running. These are in the future. Juno will be one of the most important ones. Juno will start data taking next year, if I'm not wrong. To catch results of a mass hierarchy will take 7 years, and keep it under control the energy resolution, and to have something about 3 and 4 sigma, no, not more. Okay, so all this said, you understand that it's not so stable. No, I don't want to go this. So my perspective, there are many different ways. If you make some studies on statistical side, there are different ways to define sensitivity. This is clear. If you are below 5 sigma, because it depends on your estimator, it depends how you define your errors, what is the estimator that you use, most important. So the definition of sensitivity can change from one case or the other. Only above 5 sigma, you are more or less insensitive to the statistical methodology. And this is also, Roberto, sorry, one of the reasons, because I did some study of statistics in the last years, that I would prefer to have one single experiment that achieved the 5 sigma results. And for sure, DUNE will get it. Conservative we say officially in 3 years. Optimistically, I would say in 6 months. It depends on the beam. And it depends what is if it is normal or inverse. So in a very short time, after 2032, we will be able to get a hint of the mass hierarchy, to get a measurement, a robust measurement of the mass hierarchy. And that's all I would say. The other one, I mean, if you want to be convinced how we can do it, all the measurements that we have that we have foreseen to have it. So critics, I think almost critics. Criticism, thank you. Seven minutes. Oh.
Yeah, thank you for being on time. I think we can start discussing.
Doesn't work. What you said at the beginning, so you seem very interested in cross-section measurements, no? So maybe naive argument that I've heard is that since you don't know the flux, then why improving on so how relevant it is to improve on the knowledge of the cross sections, given that nevertheless you don't know the flux. And I hope that argument is specifically which cross sections of better the cross sections need to be measured, because the muon collider may have something to say.
Okay, so about the fluxes, we are thinking for linear detectors, we are thinking to be able to measure the absolute fluxes. So this is an extremely rare, not only the relative one. It will take 4 or 5 years, more or less, because it is statistically limited, but we can measure the absolute flux, first of all. This is one thing. Then I have to admit there are other projects independent, like NUBET, for example, that you heard, that could be really important things for the fluxes measurement, of course. For the energy, you are convinced that we will do the best up till now. A very extremely good energy measurement. And then we can have a relative measurement of the cross-section at the error of few percent. But that's the point. Because sand, I mean, the solenoid is 0.6 Tesla, is right the way, the value that you need to have a precision of 4 or 5% on the momentum, on transverse momentum of the tracks. So you will be able to measure the interaction of a few percent level, the energy of the interaction a few percent level. And this has never been done. Okay. At least clear. There are projects clearly that want to measure the neutrino. There are what it is, the CERN experiment that are improving a lot. But with this intensity, with this kind of fluxes, I mean spectrum, they are not able to get the best as we have. I mean, if you are convinced, more or less. Okay, so flux, in any case, yeah, you are right. This interplay between flux and cross-section is really important. But if you disentangle, if you measure very well one, and the other one, you have the models and you have the partly an absolute flux measurement, then the game is over. For 6,
7.
for 7.
Yeah.
Nice.
So you're telling me that, again, if you measure all of these pieces in the same place,
yeah.
measure.
No.
We are integrating over.
Yeah, we are integrating
in this
over.
case. But anyway,
systematic will be below 5%.
And it's forbidden, quote unquote, to trust on the fact that you can get sigma x, the cross section over there, or any other piece. Not really from the same experiment.
Yeah, this cross section.
Yeah.
Yeah.
So
because we need
insisting on these being in situ as much as possible to not have to trust anything from another experiment, essentially.
No, but not to trust. The point is that we will be able to measure the cross section better than ever, because, for example, if you want to measure to disentangle mu plus from mu minus, you have to rely on Michel electron. You know what is the resolution, Michel, that you can get from this? 30%. So, come on, it makes no sense. You have to measure event by event. You have to measure if it is a muon, on a new mu, it is anti-new mu. And you have to measure the energy of the neutrinos in that specific interaction event by event. This has never been done. Okay, so this is our goal. I mean, this is our tool. Okay, absolutely. So this would be extremely. I mean, put a collider. Chloe was a collider experiment. multi-purpose. Put it on an electron beam, be able to put an electron beam on a neutrino beam, and you get fantastic results. But this was the idea of Bertolucci, essentially. You know?
Yeah, I have more questions on along this line, but I want to see if there is any comment from the room before.
Feel free.
Ask.
I can discuss on
an insight.
I'm open to any kind of criticism. I'm accustomed to.
Actually, you know, you're stressing that this is a very crucial experiment, and it's kind of striking to me that it's coming because somebody Chloe in the 90s essentially, and you can tell me that's how life works. I understand.
You can tell me
that's life. You know
that's life.
Chloe existed, and it looked like
it would not be possible. I mean, you have, for example, 15,000 kilometers of optical fiber in the calorimeter. It's one of the best electromagnetic calorimeter in the world, 5% of a square root of E. So you have 16,000 kilometers optical fiber. Do you know how much 1 meter of fiber, optical fiber costs now for euro? Make
many thousands now.
Yeah, so it would be impossible. That's the point. And the calorimeter is a sample of optical fiber and very thin lead layers. This is, by chance, is one of the best calorimeter that you can think for neutrino detection. And neutrino detection is one of the systematics, more important systematics in this game. By chance, you see.
In fact, I was curious if one had to improve on this detector, which is in a sense.
There is no improvement. SAND will be there, phase 1 and phase 2 for 20 years. No, that's the point. Only the tracker we can do it. Only the tracker we can do, and we can try to. I mean, for the 1 ton of liquid argon, we are just looking at the optical readout. So it would be a TPC. You don't care about the purity too much. If you improve the optical readout with a charge readout, it would be extremely difficult because they have a very intense flux, and you change the tracker with a more refined, I don't know, silicon, for example. It will be very costly. Then you can even improve this, the cross section, the clear. The cross-section liquid argon. But it will be the first detector. I'm sorry to stress too much and to have no antagonism to contribute, but I said publicly in DUNE many times, it will be the first detector to have to collect 50,000 neutrinos events in liquid argon in a magnetic field, okay? So imagine what you can do with this thing. I mean, it will be the only, because maybe some of you are sufficiently old that they heard about the possibility to put a magnetic field around Icarus, for example. Too much costly. So this will be the first detector with a magnetic field in a neutrino beam, okay? But we have a very performance, I mean, T2K also will have it clearly. If they have any detector with a magnetic field, all the UA1, the dipole, but they don't have our calorimeter and our tracker. And in any case, the resolution, I mean, is that it is. They have TPC, now we are constructing, I mean, I was not so completely fair, but you have to invite somebody from Hyper-K to tell you what is the situation of the Japanese side. I would say this is our point of view. We are working on liquid argon, and we're working very well in liquid argon. It's just time of waiting. If US and Trump will not change too much the plans.
Question trying to go in the room for improvement there, because
DUNE+, I mean, the improvement, we didn't spend any sentence about the phase 2. There is a phase 2. And the phase 2 is, instead of having the mu spectrometer, which is just a slice of scintillator and ion, very coarse detectors, you want to put a more capable near detector, that it is high pressure TPC of liquid argon in magnetic field with a calorimeter with the same performance of sand. It's just a duplication. But it would have the advantage to move off axis, so to measure different setup, different beam configuration, if you want. If we, I don't know, if we will be able to find the money, this would be the, and clearly for the far side, the phase 2 is obvious. We want to go from 2 TPC to 4 TPC because of the allocation. There is a, I mean, the cavern can allocate up to 4 big liquid argon detector. This is the phase 2. That should come out at the end of a decade of 30, more or less, 37. Okay. In time for a muon collider, I don't know. 1940, what is the time? 2040, what is the time for muon collider? No. Okay, this
I'm not the right person to answer.
Okay.
But yeah, exactly in that direction. Now, it seems you're telling me that there is no possible synergy in the sense of oscillation physics, because what's coming out of sand, it's the best possible.
No. It provides the best measurements with respect to the present one. But it is clear that, I mean, you have to constrain a unitarity matrix. Suppose, I mean, first of all, you have to constrain mass hierarchy and delta CP. They should work in some way, in a coherent way. This can be done in 4 or 5 years. But then you have to constrain the really robust, in a robust way, the unitarity matrix. You really need a measurement, an incredible, important measurement. You need a lot of statistics. The statistics that is coming out from DUNE is rather poor. Insomma, with respect to a neutrino coming from a storage ring, a muon storage, it is orders of magnitude, if I'm correct. So we really, I mean, look at think at Bell and Babar. How much they improved the measurement of mixing metrics. So it would be extremely important to have a very refined. It will come after Hypercamiocan and DUNE. This is clear. I mean, DUNE, we are talking on 5% in the previous slide, systematic. DUNE would like to reach 3%, putting all together. I don't know. I mean, if you have a full near detector complex, maybe we will be able to do it. That's clear. But there is always room for improvement, and we need improvement after DUNE and Hyper-K. In terms of statistics,
asking, was the first paper mentioned this morning that it contained some estimates of this? I may maybe not remember exactly what was the. Yes. Okay. Maybe we should have a look more, in detail. But after DUNE. Yes. Okay.
Don't say that you are using. There is no synergy.
Second one. Don't say what?
Don't say that we have no synergy with the future. Absolutely. Okay. This is the first step. We are entering in the phase, as people say, we are entering the phase of precision physics for neutrinos. But we are not coming out in 10 years. I mean, we are just entering the phase of neutrino physics. Because first of all, we want to measure the schema, the schema, how it is, how it works. If there is delta CP, what is the ordering? Then you are entering some precision, but we need to work a lot. I mean, to work a lot, to have a lot of further steps. Okay.
Do we have further comments? I think you are going to be around today, right?
I'm here until tomorrow evening. So if you have a question, no
we
problem. We can have discussion.
For sure more discussion.
No problem. Yeah.
I also have two bad questions to be asked in public on some of your plots, but
okay.
Let's keep it for later. Well, I don't see any raised hands. So I think we thank Luca once more.
Okay. Thank you.